Hello everyone, Miss Butler here. I am hyped because the Bears just came back and won the first game of the 2020 season, and so I'm celebrating by making this video about kinetics. So this is our introduction to kinetics video. Our goal this unit is to look at the rates of chemical reactions and to really pay attention to the finer details about how particles collide and how that can influence the rate that a reaction occurs. All right, so if you look at this reaction, we're going to keep it simple. A goes to B. So we're starting at time 0 with only A particles, those are the red ones. And then after 20 seconds, you'll notice we have less of the red A and more of the B, which is blue. After 40 seconds, even less of the red A and way more of the blue product B. And so this little statement says the average rate of the reaction is equal to the change in concentration of B divided by the change in time. So what we can pay attention to here is we know that B is appearing, so the average rate is going to be overall positive, and the reason that is because moles of B, that change, is B is appearing, right? We are making some B, and so we'll see the change in the amount of B divided by the change in time, or we could look at it from the perspective of A. So we can take the negative, or I would say the average rate, we would put a negative sign, and that's why this minus sign is right here, because A is disappearing, so we can see the change in A divided by the change in time, and that would be a negative average rate because it's disappearing. All right, so here's what I would like you to do. I want you to count the red particles at t equals 0. Whoops, let's try that again. At t equals 0, I want you to count the red particles at t equals 20 and count them at t equals 40. Pause the video, count up the red particles. All right, hopefully you got 100 particles. And then I got 60 particles. And then when I counted, I saw 30 particles. So what we can do here is we can look at from time equals 0 to time equals 20, we can figure out the change, or we can figure out the rate by taking the change in particles between those times, so our change is 40, divided by the change in time, which is 20. So that's our rate, and because we're looking at A, it would have a negative sign in front because the particles are disappearing. We could have also done the same with blue particles to compare. So if you look at t equals 0, there were 0 particles, and at t equals 20, there were 40 particles. So you can see that the change there was the same. We went from 100 to 60 for red, a change of 40. We went from 0 to 40 for blue, a change of 40 over the same amount of time. The only difference is the rate for the blue would be positive and the rate for the red would be negative. Negative because it's disappearing, positive because it's appearing. All right, so what I want you to notice here is this is data for a reaction with a certain chemical, C4H9Cl, with water over time. So we have time that's being recorded, and we have the concentration, the molarity of the C4H9Cl. Don't worry about the rate right now. Here's what I want you to think about is I noticed that the concentration of this chemical is getting less and less and less over time. So it's decreasing, it's being used up. What I would like you to do on your notes packet, you should have on the next slide, not this one, but the next one, you should have a graph. I want you to graph at these times this concentration for me. So pause the video, please take a moment and graph these time values and then the concentration. All right, so I did the same that I asked you to do. I looked for time and concentration and I created the graph. So hopefully yours looks similar. Using this graph, I'm going to explain what instantaneous rate is. So this is the rate of a reaction at a specific point in time. So when we have a graph like this, and I ask for the instantaneous rate, meaning the rate just at this hot moment in time, we are going to take the slope of the tangent line. So the first thing I would like you to do is find the instantaneous rate at time equals 600. So right here, whoa, right there. And then I want you to find the instantaneous rate at the beginning of the reaction, so at t equals 0. So a tangent line right there. Okay, so we got a tangent line there. We got a tangent line here. Remember, a tangent line just kisses the line. It doesn't actually intersect it or go through it. So what I can do is I can extend this guy, right, and find some nicer points. Pretend that's a straight line. I can find the slope of that tangent line using some nicer straight line points. So hopefully you have a ruler you can use, but you'll find 2 points, y1 minus y2 over x1 minus x2, and you can find the slope of the tangent line at that point. So I want you to do that. Find these two. Make sure we can find instantaneous rate by using the slope of the tangent line. All right, so we know a couple of things. One, we've seen now that reactants are being used up, so their concentration decreases over the course of a reaction. And we've also learned about this thing called instantaneous rate. And so if I graph the concentration of something at a certain time, I can find the rate at a specific moment in time by taking the slope of a tangent line. That doesn't come up too often, but it is useful to know because there are occasions where we want to find instantaneous rate. The other thing we're going to look at in this video is how the stoichiometry, so those are the big numbers in front of a balanced equation, how those influence the rate. So first of all, I know that these are both reactants, so MgCl2, KOH, they are disappearing, and MgOH2 and KCl, those are appearing. So my first question, how is the rate of disappearance of KOH, so of this guy, related to the appearance of MgOH2? So I'm focusing on this guy disappearing, this guy appearing. Well, if I look at the stoichiometry, it's 2 to 1. So what that means is I am going to use up twice as many KOHs to produce one of this MgOH2. So we can write a little statement, KOH disappears 2 times as fast as the MgOH2 appears. How about the rate of disappearance of MgCl2 to the rate of appearance of MgOH2? Well, those are going to be at the same because the stoichiometry is 1 to 1. So I'm going to disappear this guy at the same rate that this guy appears. And then how is the rate of disappearance of MgCl2 related to the rate of appearance of KCl? Well, you could either say MgCl2 disappears half as fast, right, because it's a 1 to 2 as this guy appears, or you could phrase it this way, that KCl appears twice as fast as MgCl2 disappears. So, using what we just learned, I want you to pause the video and try this one. We have a reaction, it's balanced already. I know the rate of decomposition of N2O5 at a particular instant, so I know the instantaneous rate of disappearance of M2O5, 4.2 times 10 to the negative 7th molarity per second. Okay, I want to know the rate of appearance of these two guys. So let's try using the stoichiometry. So pause the video for me. 3, 2, 1. All right, so first of all, my advice is let's use some common sense. So we know that the disappearance of N2O5, and if we look, this is a 2 and this is a 4. So basically what we know is NO2 appears twice as fast. So let's just double that. 8.4 times 10 to the negative 7th molarity per second. Okay, so NO2 appears twice as fast, so that's double the rate. What about O2? Well, that's going to appear half as fast because we have a 2 to 1. So let's cut that guy in half, 2.1 times 10 to the negative 7th molarity per second. Okay, so use some common sense here. All we're doing is looking at the relationship. Even though I said it's called the stoichiometry, really I'm just looking at the coefficients and making a relationship for the rate. So you don't actually have to set up a BCA table. We can discuss what if I only know the rate of O2. So I know the rate that O2 is appearing. Well, I know that this guy is going to be used up twice as fast. I know that this guy is going to appear 4 times as fast as the O2 appears, right? So this guy, if I know this, I can figure out the other two. If I knew NO2, I could also figure out. So really, these are useful problems because if you know the instantaneous rate of one of the species in a balanced equation, you can figure out the instantaneous rate of the others. All right, so I have a generic balanced equation here, and we saw early on that the rate of a reaction is the change in concentration over the change in time. And we know that if something's appearing like C and D, that it's going to be positive. If something's disappearing, it's going to be negative. And so what we can do is if I know the rate is the change in concentration over the change in time, if I know one of these things, let's say we know D, we know the rate, the change in concentration over the change in time, I know the rate that it's appearing, I can use the stoichiometry in the reaction, the balance equation, little a, little b, little c, little d, those are like the coefficients. I can use that to figure out the other one. So in years past, some kids have said that this average rate equation is confusing. Use common sense. We actually essentially solved this equation in our head in the last problem when we said, oh, well, this goes twice as fast, so we'll just double the rate. And they're just showing us rate here. Instead of saying what the rate is, they're saying it's change in concentration over change in time, which is the definition of rate, okay? So hopefully this was a good overview to teach you what instantaneous rate was, to tell you that rate is change in concentration over change in time, and to show you how we can use the stoichiometry in a balanced equation. If you know the instantaneous rate of one reactant or product, you can use the stoichiometry to figure out the others. So there's your introduction.